square root of x look like? So f of x equals 1 over the square root of x. What does the square root of x look like? Well, it looks a whole lot like, well, we're talking about x minus 2 though, aren't we? 1 over root x looks a whole lot like 1 over x. It just doesn't get there as quickly. This guy simply takes 1 over root x and moves the vertical asymptote over to x equals 2, right? And then this guy ends up looking like this. Now, we went from 2 to 6, didn't we? So think about it. Where is it possible for you to grab too much area? In other words, why would I have a divergent improper integral? If this area in here were too big, because this is where my function's allowed to take off and go to infinity, right? If this were too big, that rectangle, that subinterval that we would grab would have an infinite height, which we know it does, but the question is, just like the analogy back here was, if this garden door slams shut on y equals 0 fast enough, we get a convergent improper integral, versus over here, if this garden door, now it's a vertical door instead of a horizontal door, slams shut on x equals 2 fast enough, we get a convergent improper integral. So that's exactly what happened. So what we ended up with was the integral from 2 to, 6 of 1 over the square root of x minus 2 dx equals 4, which implies I have a convergent. Now, I'm a mathematician. I get lazy. I like notation. It makes my job easier. I don't know why I'm talking like this. I sound like I'm singing a song, and a bad one at that. So I'm going to circle my C, convergent. That tells me it converges. What does it converge to? It converges to 4. You see? That's kind of fun, huh? Now, let's stumble back here for just a second. Did you notice that I converged when I took the integral from 1 to infinity of 1 over x squared? And I diverged when I took the integral from 1 to infinity of 1 over x. So it appears that somewhere there's like a line of demarcation that tells me when I'm going to diverge, right? So if I take the integral from 1 to infinity of 1 over x to the p dx, where p is just an element of the real numbers, nothing fancy, all right? I want to know when this thing converges. And we're going to assume that we're in this family of functions. All right, so this is going to be y equals 1 over x to the p. Now, what does your spidey sense tell you? Well, let's discover a little bit. How about the integral from 1 to infinity of 1 over x to the 1.1 dx? All right, let's see if that'll converge. Now, try it on your own first. Just give it a shot. Relax with it. Try to do the whole limit thing, and I'll meet you back here in just a sec, and we'll see how you did. We'll do it together, okay? So enjoy. All right, hopefully you tried that out. So what's the first thing we're going to do? This is going to equal the limit as t goes to infinity of the integral from 1 to t of 1 over x to the 1.1 dx, and I might think of that as x to the negative 1.1. It might make it easier, right? So this equals, let's see, the antiderivative, if I take the limit as t goes to infinity, what's it going to be? I'm going to add 1, and I'm going to divide by what I get, right? So won't that give me x to the negative 0.1, negative 1.1 plus 1 is negative 0.1, and I'm going to divide by negative 0.1, and I'm going to evaluate from 1 to t. Now I'm going to clean this thing up because you guys know me better than that. But I could check it if I had to. If I take the derivative of this, what will I get? I'll get negative 0.1 x to the negative 1.1 divided by negative 0.1. That'll work, right? That gets me where I need to be. So I'm good. Remember, you can always check because every now and then, especially with like decimals and things like that, you might do something funky. I do all the time. So I'll check my work if I think something hoopty's going on. Okay, so I'm going to clean this up a little bit. This ends up being the limit as t goes to infinity of, just for algebra's sake, I know that if I'm dividing by negative 0.1, that's the same thing as multiplying by negative 10. And then I don't have those god-awful decimals to deal with, right? This is going to be x to the negative 0.1, and I'm going to go from 1 to t. So this ends up being the limit as t goes to infinity of what? Negative 10 t to the negative 0.1, right? Minus negative 10 times what? 1 to the negative 0.1. Now, we've got to be real careful here. Let's follow this trail up here. Wow, I just wasted a bunch of paper. This ends up being, now, it's going to be the limit as t goes to infinity of, I guess you don't waste it if it's digital, right? Sorry, it's a non sequitur, of negative 10 over t to the point 1, isn't it? Do you agree with that? Because a negative exponent drops it into the denominator in this case, plus 10, well, just plus 10, right? Because 1 to the anything, except infinity, right? Remember those indeterminate forms? 1 to the anything is 1. I got this negative, negative. I'm respecting my negative. And I end up with 10. Yeah, well, that's a trip. So in other words, this function, this 1 over x to the 1.1, shuts down. The garden gate closes down on y equals 0 fast enough that when I start gathering up, when I start heading out to infinity, I'm not picking up any real values. They're not big enough for them to add, for me to be able to add up to infinity and to have it get loose, which implies that this thing converges. So I'll ask you again, what does your spidey sense tell you? What seems to be the p-value, if I go back to my original question, what seems to be the p-value that's going to make us diverge? Well, let's figure it out. Hopefully you thought 1, because clearly 1 over x didn't work. All right, first things first. What do we know for sure? Let's do kind of a formal proof. I got to get this big old line out of my way. I can't work like this. All right, so I'm going to get this out of the way. I'm going to prove this guy. And we're going to figure out the value of p that works. So if I take the integral from 1 to infinity of 1 over x to the p dx. All right, 1, let's do this case-wise. If p is what? Is less than 0. In other words, if p is negative, what's that do to this denominator? Well, it's going to flip it into the numerator, and I'm definitely going to diverge. Now, I no longer look like one of these guys. Now, I look like one of these guys. I look polynomial, don't I? X to the third, x to the fourth, x squared, etc., etc. So this is definitely going to diverge. No doubt about it. So I don't have to worry about that. All right, so let's just see what happens. If I take the limit, this equals the limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx, right? This is equal to the limit as t goes to infinity of, now think about that. Again, we could think of this as x to the negative p, right? So this ends up, now just bear with me for a sec, doesn't this end up being x to the 1 minus p, or negative p plus 1, divided by 1 minus p, evaluated from 1 to t. Right? Does that make sense? All right. Excuse me. Now, let's see what we got to do here. So what's going to happen here? Well, if you're confused, let's just hold up. If I take the limit as t goes to infinity of t to the 1 minus p, all I'm doing is standard issue integration. Remember, x right here is my independent variable, so that's what I'm plugging stuff into, right? So it's here, I get this, and then minus, well, I'm going to get 1 to the 1 minus p over 1 minus p, right? Okay, well, that's cool. So think about this. This already tells me that p cannot be 1, right? P can't be 1, because if it is, all hell breaks loose, and I end up with a 0 in the denominator. So we could throw that in as a case. So case 2. If p equals 1, we diverge. We already proved that before. Okay, so think about this. How did I get these integrals to converge? Well, when I take the limit, when the limit as t goes to infinity of t to the 1 minus p is taken, what has to happen? I need to send this guy into the denominator of a fraction so that as t goes to infinity, it blows up, right? Well, how do we do that? That happens when 1 minus p is negative, right? So when 1 minus p is less than 0, which implies that p has to be greater than 1. You see what I did? I just added p to both sides. If p is greater than 1, that tells me the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1. Else, that's just fancy math speak for or else, it diverges. We've got ourselves a rule. It's a power integral. It's a p integral is what we can call it, because it's 1 over x to the p. Now, please understand, let's make sure, I'm going to change colors just because I know you're going to freak out. I got a lot of stuff going on here. Notice dx and x. So as far as the integral is concerned, this is a constant. And as far as we are concerned, it's a constant. It's a constant that if I want the integral to converge, it has to be greater than 0. I hope that was helpful. We're going to have some fun with these. We're going to do a bunch of these in class. So I'll see you in class tomorrow. Well, oh, I'm sorry. I got one more thing that I'm going to go over with you here in just a sec. But I wanted to give you sort of the basics on this. All right? We'll see you in a sec.